All right. Do you know how to prove this lemma?
It's number 2.
So that's not the combinatorial Nullstellenzats, but it basically proves the two statements of combinatorial Nullstellenzats. So basically what it says is if you have a polynomial with n variables, right? And ti is like the degree of p in each variable. So if you consider it as like a polynomial in one of the variables, yeah? Okay, and then if you take a bunch of sets S and they all have bigger size than the degrees, yeah? So like the size of S is bigger than T. Yeah?
Anyway, what are the sets called?
Sets of coefficients. Well, there's sets of like if it's a real polynomial, they're real numbers. Yeah. So stuff that you're like allowed to sub into the polynomial, basically. Yeah.
What's S?
So Si represents the stuff that you're eventually going to sub in for Xi. Yeah. And then and if you have a bunch of sets like that, and you always get 0 when you sub it in, right?
Or anything from each set.
Yeah.
Like, then P if you take anything from set Si for Xi, and then anything from set.
Yeah.
Okay.
So because P takes in n tuples, right?
Yep.
So if you just take in an n tuple of S's, and they range within these sets.
Yeah.
Yeah. Then the conclusion is P is actually 0.
Oh.
Yeah.
Oh, so you have enough shit going to 0, then it goes.
Yeah. So in the n equals 1 case, you already know this. See, like if n equals 1, right? Then you just have one polynomial, one variable, yeah?
Yeah.
Just like,
and it has degree, like
it has
degree. Oh, it has
degree.
more things going to 0 than degree.
Yeah.
Yeah.
And then S is bigger than T. So there's more zeros than the degree. Yeah. Yeah, there's like the product of sets. Like you know how like it's like R cross R is like pairs of.
Oh my.
We don't have any public liability insurance.
Then the S is greater than the degree. That's Leo's toy.
Yeah.
You should guess what I mean.
So the cross notation is just product of sets. Yeah.
Yep.
And I guess it's called a cross because the sizes multiply. That's probably why they got the sets are characterized by their size. Yeah. Okay. So if n equals 1, then it's obvious. Yeah.
Wait, so S is greater than T.
Yeah. So if n equals 1, there's only one S and there's only one T and then one variable, right? And because S is greater than T, so if you have a polynomial of degree n and you sub in n plus 1 things and they all get you 0, right?
Oh.
Then that means the polynomial is 0.
Yep.
Yeah. Well.
About that.
Well, one way to think about it, I guess.
It's like what's called the.
A polynomial has of degree n has at most n roots.
So there's you sub in n plus 1. Fundamental.
That and then.
Yeah. Or like if you think about it, if it has n plus 1 zeros, right? You kind of have to factorize it n plus 1 times.
Oh.
So you have degree n plus 1. Yeah.
Fundamental theorem.
Okay.
Yeah.
So it appears last week needed to be reviewed.
Yes.
Okay, and then we can do an induction on this, okay?
Yes.
So do an induction. So what do you have?
So assume n equals k is true.
Actually, maybe it's easier. I think it was easier to understand if you did n equals 2.
Oh yes.
So you have
P of x y.
P of x y. And you have tx ty.
Yes.
And then s. Yeah, I think I understand what's going on now. So xx is greater than tx. S y is greater than ty. Yeah.
Yeah.
So your polynomial is just some bunch of like so it's a bunch of like
random stuff.
px's times powers of y, yeah. I mean.
Yeah. Oh yeah.
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 So if it's a bunch of px's times the powers of y, right?
It's like the one case.
Yeah.
Oh, then you can fix.
Yeah, you can fix an x. Yeah.
Yeah.
So fix.
It's true for that fixed.
Yeah, fix an x. So you fix an x. So you fix an x as like something, right?
Mhm.
And then now it's just a polynomial on y,
Yeah.
right? And then for that fixed x,
You
have more roots than degree.
Yeah.
So that's a zero polynomial on y, right?
Yeah.
So then
Okay.
so
Now
these
you just
things are
leave-
all zero when you sub in that value. That's what that means, right? So this pi of x, the pi of si is equal to 0.
Wait.
Yeah, so like the zero is so the zero polynomial on y, right? Just means all the coefficients are 0, right? And the coefficients are these pi si's.
Oh.
Oh.
Yeah. Okay, maybe I should write this again.
Okay. Yeah.
So you sub in the si, right?
Yep.
And now it's just a single variable polynomial. And it has lots of roots, right? Because you have this many roots.
Oh, those.
And so then this becomes the zero polynomial. Yeah?
Yes.
And so the coefficients are now
So all
0.
the coefficients have to be 0.
Yeah.
Oh, okay.
Yeah. And but there's too many s's here as well. Because the degree of these pi's
It's ti.
is
and this
ti, yeah.
Wait, are we
Or it's
giving?
less than ti.
Less than ti.
It's less than tx, yeah?
Yeah.
The degree of pi is less than or equal to tx.
Yeah.
Right? Because tx is the maximum degree of all the
So by
x.
si you mean x.
Yeah, sx.
Wait, hold up. Are we giving those two? What's it called? Or is that what we're trying to prove?
Huh?
Like for these two, are we giving them or are we trying to?
Yeah, we're giving that.
Oh, we're giving them,
We're
yeah.
giving-
Yeah, that's the thing on which this all rests. There's too many roots. And what does too many mean? More than degree. Okay, so if you want to do an induction, right? You have
We're just trying to make it in terms of the previous
p equals sum
one. Wait, then when you just
pi x1 xn minus 1 x to the n to the I, yeah? Yeah.
Yes.
And then you sub in,
And you just sub in like you just fix those things.
fix these, right?
Fix these.
Right, and then now it's just a single variable polynomial.
Yeah.
Indeed.
And then the rest and then after so you know that's 0 again.
That's 0,
You know,
yeah?
each of those are 0. And then by the thing you know
By
that
the induction hypothesis.
there was 0.
Yeah. The multivariable polynomials. Suddenly that became the theme. We did it with symmetric polynomials, these polynomials. And somehow it all ended up as Combi. So this is equal to 0 for all s in n minus 1, right?
Yeah.
So that's the induction hypothesis.
Yeah, that means the whole.
So it's a 0 in that this is 0
Yeah.
for all of those, which means that by the hypothesis that's actually just 0. So everything's just 0 anyway.
Yeah. Yeah, because if all the coefficients are 0,
Then it is 0.
yeah, if they're the 0 polynomials, then they'd be 0 even if you didn't sub in the s's. Yeah, so yeah, and the induction hypothesis, I guess you just have to check that the degree of pi in each of the variables is actually less than or equal to ti. Not tx. Like,
I guess that's just like assumed.
yeah.
Yeah.
Yeah, I guess it kind of can be tricky because it's not equal, it's always less. But you just need it to be less. Right.
Oh, so it's like when you put in like sub in si to s1 to sn minus 1,
Yeah.
it just means like sub in any like anything.
Anything's in those sets, yeah.
So you just sub in one of any like those, and then that comes out. So you know that coefficient's 0 in those. And wait. Oh, I kind of see what.
Yeah.
So then like PR, because you repeat that for like all the all the like S1, all the sizes.
Yeah.
So then now you have like a very large amount of things that work for that.
Yeah.
So when that thing's zero for that many things, then you know that's a good.
Yeah. So if you keep going down the induction, you got another like QI with Sn minus 2.
And then you end up.
Yeah. Are we happy with that? All right. So let me